So I have started recording. You can find a lot of information, and most of the details that you can find on the internet, they are taken from this book, from the Builder's Guide. It's called Climates. Okay, but look at this. You can find a lot of examples, hand drawings, computer drawings. You can find a lot of examples. And if you have any questions, let me know, because this is how you will learn. So I assume that you don't know everything about this kind of detail so far. For example, this one, it's quite good because we have a brick wall here. And on this brick wall, then we have the rigid insulation. We have an air cavity between the rigid insulation and the brick wall here. And then we have the thermal insulation here. And then we have the interior finish, which is a ½ inch of gypsum board. Okay, so basically it's the same detail as we studied before, but here we have the air cavity, and instead of the shingles, we have a brick wall here. If you're working with your own building, you have to decide. It's your decision. It's not mine. It's not even your design instructor's decision what kind of materials you want to work with. It's up to you. So if you want to work with brick, that's fine. If you want to work with natural stone, that's fine. Wood, okay, concrete, whatever. Then based on that decision, we need to analyze and we need to calculate the U value and the R value and all that. But especially the interior and the exterior finishes, they are up to you. So we are not making that decision for you. You can ask me, okay, do you think brick is a good option for this kind of building with this kind of wall, with this shape? And then I can give you my advice. But first, you need to ask me if something is good or something is the right or not the wrong. There are no wrong decisions here. It's just the best or not the best decision. That everything can work. If you want this to be by a brick wall, okay, that's fine. What if you want a curtain wall? What if you want something like this? This is a building that we're going to study today. So what if you want an envelope like this? Perfect, that's fine. Is it the best option in Keene, New Hampshire? I don't think so, but it depends on what kind of building you are working with, okay? So just try, do a research, and let me know if you have any questions about this. When it comes to roofs, probably roofs are more complicated. So if you are working with roofs, the first decision that you have to make is if you want a flat roof or if you want a tilted roof. And roof details. Okay, so first we have the system. This is the system that we have studied with rafters and thermal insulation in the middle. Okay, so those are the rafters. So this is the kind of detail that we have studied on the first assignment. Okay, that's fine. Here we have the structural elements that we need thermal insulation between these two structural elements, and then we need the internal finish and an external finish that usually we have shingles outside. Okay, so first we have to decide the system, and the first option is do we want this or do we want a flat roof? If we want a flat roof, we have other options. We can work with concrete. This is more a commercial building detail, so we have a lot of layers, but we always have a structural element, and then we have thermal insulation, and then we have an external finish. So if you have flat roofs, things can be different, because with flat roofs, yeah, so we have to get rid of water, and getting rid of water in flat roofs, it's complicated. But there are other options with, okay, so basically if we are working with the same kind of detail, The roof, it's the same detail. We only need shingles. Roof shingles can be metallic roof shingles, made of ceramic, asphalt, whatever, but we need roof shingles. Then we need another rigid insulation here. And then we need the thermal insulation where the rafter is. And then we need a gypsum board or interior finish. So details of the roof and the wall, they are quite similar if we are working with this kind of construction. If we are working with it with other construction method, okay, so if we are working with this framing, the details of walls and roofs, they are, but if we're working, especially we're working with, or even, okay, so this is a flat roof in which we have the beams or the rafters, and then yeah, we have a board here. We have a thermal insulation above. Here we have the thermal insulation between the rafters. My advice is that you should have thermal insulation between the rafters, and then you need extra thermal insulation above to reduce the U value. Okay, but as you can see, you have a lot of information here with nice drawings. And even, Emily, there's another option. If you don't want to do it by hand and you don't want to do it using Revit, you can copy one of these and paste it on your project. If it fits your project, I will accept it. Okay, so here you have a lot of information. You have the names and you have nice hatches. And so do a research, but it's always the same. We have the thermal insulation between rafters, then we have extra thermal insulation outdoors, and then we have this siding or shingles. We can have air cavities or we cannot have air cavities, so it depends. But it's 80% of residential buildings, they have the same kind of construction detail. Okay, so go ahead and let me know. And please do not get stuck. If you don't know what to do, email me and I will help you. But first, try to do something on your own, and then ask me if you have decided it's right or wrong. Do not ask me, okay, what do I have to do? Try to make your first decision, and then I'll help you. Okay, so when it comes to details, you can either use this builder's guide to code climates. That's good because we can, all the details that you can find on that book, they are correct, so they are good. So on the internet, we can find good things, or we can find things that are not as good as we expect. So that's why I'm here, to help you decide and to help you select the right detail. So I was explaining the part one. So we're talking about the first sketches of walls, roof, and basement. So again, the first sketch, then we will change it, but we have to start analyzing something, and it can be right or wrong. If it's wrong, we will change it. Doesn't matter. And finally, we need to calculate the U values of walls, roof, floors, I would say basement, and windows. So for windows, I told you that we might need start this exercise with a window that it's not a high performance window. Okay. So if we want to do this, I can, this is the Fisher house. No. Okay, I don't think I have posted that, but I will do it. Okay, so this is a detail taken from, this is a basement. So we have seen, or we have looked at the walls, roofs, that would be a basement. And I think it's a good option that we have an insulated basement. So you know that there's an option to have thermal insulation only up to 1 or 2 or 3 feet. But I think if we continue this external rigid insulation here, that is the best option for a basement. Then we have other things that probably we don't know yet, or you don't know yet. So those drains, okay, so we will talk about these later or probably in other courses. But if you analyze this, we have, again, we have exterior siding, we have the rigid insulation, then we have the thermal insulation here, the internal finish. And here on a basement, we always have a concrete wall. We can't have a wood or a framing wall here in the basement. We need something solid to bear the weight of the soil here. So that's why we always need a concrete wall. And I would extend this layer of thermal insulation all the way down to the footing. Okay, so I think that's a good way to start with the basement. And when it comes to windows, I have pasted here. So here we have single pane, double pane, double pane with low emissivity, double pane with low emissivity and argon field, triple pane, low emissivity and argon field, quadruple and quintuple panes. Well, I haven't seen a quadruple and quintuple, okay, but triple pane or triple glazing, yeah, I think it's, so we should start our analysis with this double plane air field. Okay, so I would use a U value of 0.49 in BTU hours Fahrenheit and feet square, this one. And for the improvements, I would use this one, the triple pane with low emissivity and argon field. The catalog that I showed you, it's a high performance glass catalog. So they were either double pane with low emissivity and argon field or triple pane with low emissivity and argon field. But the first analysis should be with this one. Okay, so you can start your first analysis with this, and then we will move for the improvements. We will move with either double or triple, but a high performance one. Okay, I will post this on Canvas today because this is a good basement detail. And here we have the construction. We have different windows. Single pane, it's not for buildings. And double pane air field. Well, this is an improvement because in the 70s or in the 80s, people were using, or architects were using single pane windows. Then they moved to the double pane, but now we are one step farther and we have to go to the high performance glasses, either this one or that one. Okay, so the U values of walls, roof, and windows. Yeah, let's move on. So for the windows, you can use that catalog. And for the roofs and walls, you can use something that is below R value 50, R50, and then we will move to something better to calculate the improvements of the, and then you will have to submit a PowerPoint file on Canvas by the due date, and the due date is on October the 21st at 11 p.m. Yes, so I would like you to submit something by the next class so I think the due date is at 11 p.m. But if you submit something before, I can go over this and I can help you, I can give you feedback on Wednesday, because on Wednesday, the idea is that I won't give a lesson. You will show me what you have done. Okay, so this is the assignment. It's already posted, and go ahead. But I want to give a lesson today. Okay. I want to give a lesson on solar radiation analysis. Why? Because, well, sun, it's something, well, it's the source of energy that we have on Earth. It's for free. Every day it rises and every day it sets. But we have to understand what the solar radiation is, because probably is the most important external source that we have. We have wind, we have water, but sun, it's probably the most important thing when it comes to the energy efficiency of the building. So first, we need to understand what solar radiation is. Well, it's complicated. We're not physicists here. We're not studying physics, but we have to understand that within the electromagnetic spectrum, okay, the spectrum is a graphic that relates wave magnitudes or wave parameters to energy parameters. So here we are relating wavelength, which is a wave length. So we have waves, so we have the wavelength. And then we are relating the energy. Okay, so that's why we have a spectrum, because we relate wave parameters or wave magnitudes, wavelength, frequency, period. Okay, and we are relating this to energy. It can be either power or energy or kilopower. So when we're relating these two concepts, then we have a spectrum. And the electromagnetic spectrum is, well, it's everything that we have around us and we don't see. Well, what we can see, it's just the visible light spectrum, or we have this narrow band of wavelengths, and this is what we can actually see. We can see from this wavelength until this one. This is the violet, and this is the red one. Okay, so we can see 7 colors. This is our perception. Other beings, not human beings, they can see other wavelengths, and they can hear other sounds. Sounds, it's related to waves. It's another wave, another kind of wave. Okay, but our perception is limited. It's quite limited. Out of all these infinite wavelengths, we can perceive, we can see only just this narrow band of this electromagnetic spectrum. What is beyond the ultraviolet or the violet color, it's the ultraviolet, and what is beyond the red color, it's the infrared. We can radiation or infrared radiation, but we can feel it. Infrared is heat. Okay, so we can feel that we are under the sun, and we feel that our body is heating up, or our skin is heating up. And we can feel the effects of the ultraviolet radiation. We get tanned, okay, so our skin gets darker with the ultraviolet radiation. And if we are exposed to a level of ultraviolet radiation, we can end up having cancer, skin cancer. Okay, so it's not there, we can see that, but we can feel the effects on our body. But what we can actually see, it's this narrow band in this electromagnetic spectrum. Yeah, so this is what we are, or what we see. And light, it's well, it's difficult to explain, because we can explain light with wave parameters or magnitudes, but they're also particles. So in light, we have photons. Not photons. Okay, so let's say the Wikipedia. And let's say English. Oh, photon, it's PH, sorry. Okay, so the photon, it's an elementary particle. Interesting. It is the quantum of the electromagnetic field, including electromagnetic frequencies such as light, radio waves. Okay, so we have particles. A photon, it's a particle that carries light. Then it's an elementary particle. It's not an atom. It's something even smaller than an atom. Anyway, it's fascinating, but we are not talking about this. But explaining light, it's we have to explain light through wave magnitudes, but they're particles. So those photons are particles as well. Anyway, we're not explaining this, we're just explaining the effects of this solar radiation. And we have two concepts that we have to understand today. So we have the radiance and the irradiation. Sometimes we tend to mistake these two concepts. Even I will mention radiation and I want to say irradiance. Anyway, if we want to be accurate, we need to understand that irradiance is power and irradiation, it's energy. Okay, so we are dealing always with power and energy. So when we are talking about solar radiation, again, we have power and we have energy. So let me try to explain this with this graphic here. So the solar irradiance, it's the curve. So you see that we have a blue curve here. So that curve starts at the sunrise, because during the night, we don't have any solar radiation. So we don't have any solar radiation. That means that the solar irradiance is 0 because we don't have sun. Then when the sun rises, it starts growing and we have a peak of solar irradiance, usually at noon. And then it goes down again. And after sunset, we don't have any solar radiation. Okay, good. When we are talking about irradiance, okay, well, what is the solar irradiance? The next question has to be when? At noon. Okay, so at noon, the solar irradiance is this. And what about at 9 a.m.? At 9 a.m., it's this one. So we will have a scale of power here. And here we have another scale of time. And we can say, okay, at this time, the solar irradiance, it's this one. So this is a specific point on this curve. So this is what the solar irradiance is, and it's a magnitude of power units. It can be watts per square meters in international units, BTU hour per square feet in imperial units or English units. What is the solar irradiation? It's the energy. So the energy is the area that we have under this curve, and under this irradiance curve. Okay, so this hashed area, it's the energy. So that's why when we are turning power into energy, we have to multiply times time, either 24 hours or 12 hours or 10 hours, whatever. Okay, because we have the solar irradiance. So this is the amount of power that we have at a specific moment. And then we multiply this times hours, minutes, days, whatever. We need to multiply power times time, and then we have energy. So that's the difference. Irradiance, it's power, units BTU hour per feet square or square feet. Irradiation, it's energy, and the units are BTUs or BTUs per feet square. We don't have hour. Okay, so that's the difference between irradiance and irradiation. This is just an exercise, so we're going to solve this, and this is something that I'm going to post a test. Let me write it down. Okay, so I'm going to post a test to make you calculate or turn power into energy or irradiance into solar radiation. So let's solve this. So the solar power, so this is power. So if it's power, it's irradiance. Incident on a 100 square feet surface. Okay, so we have a square, 100 square feet, 10 by 10. And the solar power, the irradiance incident on that surface averages 70.44 BTU hour square feet. Okay, so these are power units. for 12 hours. So this is time. So how much energy is received? Energy is power times time. Okay. So what is the energy? The units are BTU. BTU. What is the power? The power is 70.44 BTU hour feet square. Then we have to multiply this times the time. So we are talking about 12 hours. Okay, so this is 12 hours. And then if we do this, we would have a result. It's 70.44 times 12. I have a calculator here. 70.44 times 12. So this is 845 times 2 BTU per feet square. Okay. If we want to turn this into BTU, we have to multiply times the area, so times 100 feet square. So that would be 84,520 BTU. Okay. So this is the power, 70.44 on this 100 square feet or 100 square foot surface for 12 hours. And then we have to multiply everything. So we have BTU divided by hour by feet square. So then we have to multiply times 12 hours times 100 feet square. And this is the energy. This is the BTU. So the second exercise is the amount of solar energy collected on a surface over 8 hours is this 1,268 kilowatt hour per square feet. Okay, so this is the amount of solar energy. So energy, it's kilowatt hours in international units per feet square. What is the average solar power received over this period? So if energy equals power times time, power equals energy divided by time. Time, hours, energy in international units, it's kilowatt hours. Okay, so that is the energy is 1,268 and the time is 8 hours. So the result is 1,268 divided by 8. It's 158. Units, kilowatts per feet square. Okay, so here we don't have any information about the area, so we cannot multiply times area. So the units, the final units are kilowatts divided by feet square. And kilowatt is a unit of power because we are asking for the power. Okay. So I think I told you on the first lesson that I recorded back in August. I told you that if I had to decide what do you have to know after taking this course, that should be the difference between energy and power. So we are repeating this many times, and we will repeat this next semester when you are taking either solar design or if you are taking systems. We will be dealing with energy and power because it's very important to get to understand the difference between energy and power and how we can go from energy to power and from power to energy. Do you have any questions about this? I told you that I'm going to post a test on this topic, so I will post a few questions like this. So if I'm talking about energy, you will have to give me the answer in power and the other way around. If I'm talking about power and time, then you will have to give me the answer in energy. Okay, so I will post 10 questions like this, and it's a test, and you will have this week. If you know how to do it, it takes a couple of minutes. Okay, but I want you to I want you to do it because it's important, and for sure on the final exam you will have questions like this as well. Okay. Now, well, that's interesting because this is we are talking about what kind of solar radiation we are receiving here on the Earth's surface. From the sun until the limits of the atmosphere, what do we have? Well, we don't have anything. A few planets, probably a few comets and some asteroids, and that's it. That we don't have air, we don't have gas, we don't have matter, we don't have anything. So it's a vacuum from the sun until here, until this. Well, so the sun energy is transmitted by radiation, and then it reaches this outer limit of the atmosphere. So that's interesting. This is pretty thin. So it might seem that, well, the atmosphere, it's thick. Well, it's thick from a human being perspective. From the universal perspective, this thin layer that makes life happen, it's very thin. So we're very fragile because if we didn't have the atmosphere, there wouldn't be life on Earth, at least the kind of life that we know now. Maybe there will be other life, but not human beings for sure. So what's the thickness of this atmosphere? Well, so this thickness, it's around well, that's a good question. So let's find out. What's the thickness of atmosphere? 60 miles. Okay, 60 miles. So this is the thickness of the atmosphere. But where can we live? So the layer of the atmosphere in which we can live, can we live on the top of Mount Everest? We can't. Okay, so we can't live here on the top of Mount Everest. We can't. So what is the the height of Mount Everest? 5.5 miles. And we can't live here because we don't have enough oxygen. We cannot breathe without oxygen here. Well, maybe we can breathe, but only for a few times. So the thickness of the layer in which human beings can live, maybe it's 2 miles. Yeah, kind of. Okay, so we can live in this narrow layer with air and other gases that we can breathe. Other than that, human beings cannot live there. Okay, so think about it. But on these 60 miles that we have from the Earth's surface until the outer limits of the atmosphere, what do we have? Well, we have gases, and each gas has its mission because we cannot be exposed to the solar radiation as is out of the atmosphere. So we need these filters, okay? Because we have to filter this power that we receive from the sun. We cannot live without sun, but the solar radiation can kill us as well. So let's learn what kind of gases we have here. So first we have the ultraviolet solar radiation, and we have the infrared solar radiation. If we receive a lot of ultraviolet or infrared, it will have bad effects on the Earth. So we have two kinds of gases to protect us from this solar radiation. We have the ozone, this O3. Okay, so this is the ozone, or trioxygen. So it's 3 atoms of oxygen. So the oxygen that we can breathe, it's O2. This is O3. So this is the ozone. Okay. Do we have ozone on the atmosphere that we are, or where we are living? Yeah, there is a certain proportion of this ozone. We can breathe it. But again, if we had too much ozone, we would die. So it's not something that we can breathe. So we can't. We would die if we are exposed to a lot of ozone. Okay, but we need this. Why do we need this? Because this ozone layer absorbs part of this ultraviolet radiation. So it's a gas that we cannot breathe, or at least we cannot breathe a lot of ozone because we would die. But if we didn't have ozone, there would be a lot of ultraviolet radiation that will reach to the Earth's surface, and it will end up killing us. Okay, so we need a balance between the amount of ozone that we have in the atmosphere. I remember that in the 80s, I had never heard about that, but I was a kid, and everybody was talking about the ozone layer because there was like a hole in that ozone layer, and the amount of ultraviolet rays on the Earth's surface was increasing. So it was caused by CFD gases. No, it's CFC. Okay, so this is it. So where can we find these gases? We can find these gases in hairspray. So the 80s, if you have seen some movies, it was the golden age of the hairspray. Well, it was bad for the atmosphere. We didn't know that. And the other place in which we can find those kind of gases are in the air conditioning systems. Okay, so in refrigerators or in AC systems, devices, the gas or the fluid that is running through this, it's CFC. So it's another gas that it's harmful for the atmosphere because it changes or it decreases the proportion of ozone that we have in the atmosphere. Well, it makes sense. I don't know if it was for the hairspray, but in the 70s or in the 80s, the industry, the air conditioning industry, it was booming. Okay, so by releasing these kind of gases to the atmosphere, they started causing trouble with this. Okay, so there was this break or this breach in this ozone layer. So the amount of ultraviolet radiation increased at the time. What was the consequences? So the hairspray was forbidden. I think it was a good idea. And secondly, these kind of CFC gases in the air conditioning system were forbidden as well. And well, mechanical engineers, they had to came up with other gases that are less harmful to the atmosphere. Okay. But that happened in the 80s. Now we are with other issues, which is the global warming. Well, everything is related, but why is that happening, the global warming? Well, first we have this ozone. We need this to absorb part of this ultraviolet solar radiation. Okay, that's fine. Then we need clouds. So when we have clouds, the clouds are water vapor. Okay, so it's water vapor, it's something natural, and it absorbs a part of the infrared solar radiation. Okay, so by having water vapor in the atmosphere, sometimes we see these water vapors, they are clouds or fog, so we can see that. But even if we don't realize that there is a water vapor, but there is, and it absorbs part of this infrared radiation. Okay, so again, if we didn't have water vapor, a lot of infrared radiation will end up hitting the Earth's surface, and that won't be good as well. So we do have water vapor on the atmosphere, and that's fine because it protects us against an excess of infrared radiation. And then what other radiation can we have here? Okay, so we are protected by the ozone layer, we are protected by water vapor, but part of this solar radiation enters the atmosphere and hits the Earth's surface. Okay, so this part of this radiation is absorbed by the Earth, and part of this radiation is reflected. And this is what we call albedo. So this word, I don't know if you have heard of it, albedo, it's the solar radiation that it's reflected by the Earth's surface. Okay, so part of this albedo leaves the atmosphere. Okay, so it's re-radiated, especially during the day, the Earth's surface, it's warmed up. And then during the night, the Earth's surface radiates or reflects this albedo, and part of this albedo leaves the atmosphere. But, so we have a lot of rays like this. Okay, but part of this reflected solar radiation again is re-radiated back by the atmosphere. And that's good, because if we lost all this radiation, the Earth, the temperature here would be too cold. Okay, so thanks to this atmosphere, part of this albedo is re-radiated back to the Earth's surface. So that's good. But what happens if we have this greenhouse gases? Okay, so these greenhouse gases are good because they help us. These are responsible for reflecting part of this albedo. Okay, so we need a certain amount of these greenhouse gases here. So that radiation is reflected back, and this temperature is quite good. But if we have a lot if we increase the proportion of these greenhouse gases, then a lot of radiation will be re-radiated here. And well, so this is what's going on now, and this is global warming. Okay, so because naturally we wouldn't have this amount of greenhouse gases in the atmosphere, we have only the right amount of them. But if we increase this proportion, then this energy is not released to the atmosphere, it's re-radiated, and then we have the global warming here. Does it happen? It happens. I can show you a picture of where I live, where I used to live when I was in Spain. There you go. Okay, so you can see that especially in big cities, we have this. And what is this? Well, it's a concentration of these greenhouse gases, especially when the wind is not moving, when it doesn't rain, when the heating systems are on. There are a lot of cars here, so we increase the proportion of these greenhouse gases. And this is something that we can see if we walk out of the city and we look at the city from afar, we can see that something's going on. Okay, so we can see that. Well, so this is what's happening. And can we prevent this from happening? Of course we can. I mean, as human beings, we can use less fossil fuels. By burning fossil fuels, we're increasing the concentration of greenhouse gases here in the atmosphere. But by architects, we have a huge responsibility, because they say that 40%, so let me copy this. Big. Okay, it's a fact that 40% of greenhouse gas come from buildings. There you go. 40%. And why is that happening? Well, probably because the energy efficiency of our buildings is not quite good. So if we had more thermal insulation, if we include photovoltaic panels on our buildings so that we don't need to burn fossil fuels to heat up or cool down our buildings, we would reduce the amount of gases that we are releasing to the atmosphere. Okay, so it's not a question of politics. It's not a question of I believe in climate change. No, I don't believe in it. Well, we know that if we have this kind of if we increase this proportion of greenhouse gases, it can be harmful for the atmosphere. We know that. And we know that we can reduce that by designing good buildings. So there's no point about politics here. It's not about, no, I don't want electric cars because I don't have electric chargers. Forget about it. There's something we can do as architects, and we can design efficient buildings, close to zero energy buildings. So we don't need to worry about cars or transportation or planes or whatever. If we as architects can reduce this 40%, this is something that we can do. And it's not, we are not doing something outstanding. It's about selecting the right amount of thermal insulation, the right glass, the right orientation for our buildings. So by making those decisions that are for free, I mean, we don't have to spend money on making those decisions, we can reduce a lot this problem. Okay, so this is what we need to know about the solar radiation. We need a balance, or we have a balance in this thin layer, in this atmosphere. That is where life happens. Out of this atmosphere, there's nothing. Maybe there is, but we don't know. What we do know is that in these 2 miles, we need to keep the balance between all these, between the ozone, between the water vapor, between the greenhouse gases. And if we break that balance, life will disappear. So that's, or life as we know life nowadays. Maybe there will be another life, but our life will disappear. So we have to know that. But those are concerns that we need to be aware of. But I want to point out other things that affect architects, and probably not other people, maybe artists or people that take pictures, that especially affect architects. It's the quality of light. Okay, so we are talking about light from the, or solar radiation from the thermal or the energy point of view, but we have other points of view, and they are relevant to architects. Okay, so I have the, I'm going to paste this on the browser, because I was preparing something about this, and I have found this website, Arc Daily. It's a good one. You can look at a lot of projects. They have products you can download, and they have news, and you can upload your own projects if you are proud of them and they are good enough. They will be posted here. But I found these interesting articles on 10 typologies of daylighting, from expressive dynamic patterns to diffuse light. Okay, 10 typologies. Why 10? Well, the number 10 is cool, so that's why everybody is out 10 commandments and 10, well, 10. We have 10 typologies of daylighting. So look at this. So this wouldn't be the same without daylighting. Okay, so we have this pattern in the envelope. Is this a roof or wall? I don't know, something between a roof and a wall. But the shadows that this pattern or these elements are casting on the floor, not only on the floor, but on everything. So it creates what this building is about. This building, by the way, is the Seattle Library, the Central Library of Seattle, or the Seattle Central Library, I don't know. It's this weird building. Okay. As you can see, it's the envelope. So we have a weird shape, and this shape is, well, we have these structural elements, and then we have glass. So this is, and then this is the building inside. We have different volumes. So they have created those volumes, and then they have an envelope to cover all these volumes. And the most interesting spaces are the spaces that are between the volume itself and the envelope of the building. Okay, so that's why we can create those lobbies. Well, outstanding. But again, this is outstanding because we have this, we have the natural light in this pattern. So we have the sunlight, and we can create this pattern here. Okay, and we have different views of this building. Okay, cool building. Who is the architect? Well, it's not an architect, it's a firm. This is OMA. It's a huge company. I think it's the best architecture firm on earth right now. And I want to show you this because I love this website. So when I grew up, I want to have a website like this. Okay. Well, they have a lot of projects, but regardless of the projects that they are outstanding, I like the website because you click on each project, and here you have all the information. You have first a nice picture. So this is what the cover page is. Look at this about the presentation. If you want to present your work, what do you need? The best picture on the cover page. Or if you are designing a website, you need the best picture here, okay? And then you have information. Yeah, we need the location, interesting, the client, the year, whatever. And then you have other pictures that maybe are not as relevant as those one, okay? But the best picture, it's up front. And you can find this in every single, okay, so we have I don't know if this is a render or if it's a real building, I can tell. This is in New York, by the way. Well, that's interesting because here in New York, we have this building, outstanding, by Kazuyo Sehima, Japanese architects, this one. And this one is new. It wasn't there last time I was in New York. And this is by OMA, this one. Okay. Yeah, I think they like this idea of having like different volumes, and then they have a continuous envelope. And they have their staircase here on this. Yeah, it's the same idea. They have the lobby on this. Beautiful. Okay, but we're not here to, well, we can. Who's behind this OMA, this OMA office? His name is Rem Koolhaas. The guy. Well, when I was a student, he was like this, but I think nowadays he has lost a lot of weight. Anyway, Rem Koolhaas is probably the most, in Europe, everybody's crazy about this. So every single European architecture student wants to work with for that firm, even for free. He's in the Netherlands, and there are a lot of architects that go there. Please, can you hire me for a year or 3 months or whatever? I want to get paid, but I want to work for you. And he says, okay, sure, you can go ahead. Anyway, a great architect and an interesting guy. But I was talking about this. So I was talking about the typologies of daylight. And I like those pictures because looking at those pictures, we can see that the space is different. And the space is not different. It's just the same volume, but it changes because of the light, or because of what we are doing with the light. So we can have something diffuse, or we can have these dramatic lights here, okay? So I like this exercise, and I like the way it's shown here. So that's why he is talking about from expressive dynamic patterns. So this is an expressive dynamic pattern because the sun is moving, so the shadows will change throughout the day. Okay, so we have this dynamic concept of light because as the sun is moving in the sky, then the shadows are moving as well, and we have this thing. But when we have a diffuse light, then we have a space like that. Okay, so it's completely different. For example, if you are designing a yoga studio, it's a place in which you don't need an expressive, dynamic, whatever. You need something peaceful, quiet. And I think this kind of light goes well with a yoga studio. This kind of things go well. This is a lobby, so there are a lot of people moving because this is the lobby of the building. Okay, so there are a lot of people walking, going upstairs, downstairs. So when you have movement, these kind of effects are quite good for this. But if you want a quiet space, peaceful, nothing matters, you can only hear the birds chirping or like this. So you need a diffuse light like this one. in my opinion. Okay, but and I like this idea because look at this. We have the same shape. It's just a rectangle, and by using different skylights or different things, the outcome is completely different. So here you can see how this space changes just by changing the way we introduce daylight in this. Okay, and here we have I like this schematics, this one, because here you can see that we have 10 options, 1, 2, 3, 4, 5, 6, 7, 8, 10. And these are the effects of these options on the space. Okay. So I like this picture because I think it summarizes everything. So here we have this dramatic pattern that changes throughout the day. With this kind of skylights, we can create this diffuse light here, or well, we can create different patterns with different. I don't know. I think it's a cool website. And if you are designing a space now, what do you want? Okay, so if I ask you by Wednesday, okay, what kind of daylight do you want in your space? First, what is the use of your space? Is it a yoga studio? Okay, so I wouldn't do this for a yoga studio, the option number 1. Well, I don't think so. I have never been to a yoga studio, but I don't think they want contrast between light and shadows or whatever. No, they might need something different, probably something like this with diffuse light. We don't know where the light is coming from. Okay. But if we are designing a single family house and we have a nice view on the south side, probably we would need something like that. We need, this is what, if we look at the houses that I have shown you, the Escherich or the Fisher. Okay, so they have this on the south side and they have this on the north side. So I think they are using this option. So they have opened this glass wall on the south side and the rest of the windows are just, they don't matter. What about this one? Well, interesting. If you look at this guy, light-skinned. There's a museum in Berlin. Okay, so his option is this kind of openings. So they are not windows, so they are like cracks in this volume. Why? Well, we need to know about this museum, what the idea behind this museum is. But I think he has decided on this kind of light. Okay. What about this one? I think the best example that I have for number 9 is it's this. Okay, so this is a workshop, and people working in a workshop, they need a lot of natural light, but they need this diffuse light. We don't need a dramatic light on our faces when we're working on a workshop because we need to concentrate on our task. So we need enough natural light, but we need this. And how did he create this effect? It's just by using these beams. Okay, so as you can see, those beams, they let the northern light enter the building, and so this is the explanation. Okay, so we have this element here, so we have a place in which we have light, but it's from the north. So if it's light from the north, we don't have shadows, so we have this kind of diffuse light. Okay, yeah, so this is the elements they are using. So the light enters through this here, and this is north. Okay, I think this is what they wanted with this option here. There are different options, but depending on what you want, you have to decide. There are 10 here, maybe there are more, but I think 10 are more than enough. for you to make a decision. So on Wednesday, I would like to ask you what kind of light you want. If you're working with houses, with the 2 houses I provided you with, I think this is the option number 5, or probably option number 4. Yeah, between 5 and 4, this is the option. But what do you want? So what option would you want for the space that you are designing now? And if you don't have enough, I want to show you this. Okay, this was my teacher. Well, this is my teacher's work. Let me see if he has a picture. Yes, this guy. Huh. What are you laughing at? Anyway, he used to be my teacher, and well, it's interesting because he's making the most of this. Okay, so he's decided what kind of light you want in that space, and then he does it. I think he literally translates the options that we have seen here. Okay, so in this picture I'm showing you, it's the first option. So they have this dramatic daylight that is changing throughout the day in that space. This is a lobby, so I think that goes well for a lobby. This is the lobby of the building, and I think this goes well for that lobby. But in other buildings, we might need something different. Let me see. Okay, for example, this one. If you are designing a sports facility, you want kind of a diffuse light. You don't need this dramatic light, because if you are playing basketball or you don't need contrast between lights and shadows, because it's disturbing. Okay, so you will need that kind of diffuse light. And I think he has a sports facility. Well, I don't find the picture of that facility now, but it's clear that light matters. Okay, so it's another material of architecture. So it's not the floor, it's not the roof, it's light. So it's like another material that you have to keep in mind. Anyway, first we need an idea what kind of light we want in our building, and then we can start analyzing the energy that we need. I think this is the sports facility. Yeah, but it's too small. You can see that. So we need an idea, and then we need to calculate the energy that is associated to that light. Okay, but we need to balance between what we want to do and then the energy performance of the building. And if we have the right light, it's not the amount of light, it's the quality of light. Okay, so and I think these 10 options are quite good, because yeah, so go over this, and I think these 10 typologies, I'm sure that you can find the typology you are looking for among these 10 typologies. Okay, so just go over that website and use these kind of things for your design. And then once we have made our decision about the kind of light, the quality of light that we are using, then we can start calculating the thermal and the energy parameters of light. But we have to connect the project, we have to connect our idea to the energy performance of the building. Okay, so this is the diffuse light. And now we need to know about numbers, okay? Because we are working in the United States, and we have data. We have the average daily solar radiation per month. So in June, I think it's quite similar. throughout the country. Well, maybe in Alaska they have less daily solar radiation. In December, it's different. So in December, so they are here in the southwest, they have a lot of daylight. That in the north, in northeast, we have very few solar radiation. So we have to make the most of it. Okay, so probably in this area of the country, we have to get rid of solar radiation because there is a lot. But here we need the solar radiation because we don't have enough. And okay, so by looking at this data, we can understand where we are. And when we understand where we are, the use of our building, then we can make a decision about the quality of light we need. And I want to finalize by showing you something at a bigger scale. So this is the sun and this is the earth. And this is a plan view, okay? So this is the earth revolving around the sun. I'm not going to ask you today, but when I ask that question or this question to other students, I always have the wrong answer. When I ask the question of why do we have seasons? Why do we have winter and summer? So there's always a student or 2 or 3 or 10 or 50 that say we have seasons because in winter the earth it's far away from the sun, and in summer the earth it's closer to the sun. Right? Wrong answer. So this is the orbit of the earth around the sun, and it's not a circle, but it's almost a circle. Okay, so the distance doesn't make any difference. What makes the difference is the angle. And okay, this is what we have to understand today. If this is the orbit in which the earth is revolving around the sun, so we have this orbit, this horizontal plane, the angle, the north to south angle, is tilted here. And this angle, it's 23.5. Okay, so this is what we call the solar declination or the ecliptic angle. By the way, the ecliptic, it's this plane here. Okay, so this horizontal plane is the ecliptic. So this is the plane in which the earth is moving around the sun. That this is not parallel to the equator. So this is the equator, and we have this angle of 23.5. Okay, so we need to know that. And by the way, this angle, according to, I think it's moving. It's moving like, I don't know, very little every 10,000 years. It's moving well, a little. So we don't notice that in our life. But I don't know, in millions of years, the earth will be upside down, and I don't know what will happen. But this is not something that we can control. We can control the greenhouse gas emissions, but we can't control the tilt of this axis. Okay, so we need to know that. Look at this. We have the tropics. And why do we have the tropics here? Well, it's interesting because we have this intersection between the ecliptic plane and the Earth's surface. So when we have this intersection, we draw this line parallel to the equator, and then we have the tropics. Okay, so the Tropic of Cancer, the latitude of the Tropic of Cancer is 23.5 north, and the latitude of the Tropic of Capricorn, it's 23.5 south. Okay, and why is that important? Well, I don't know. Tropical countries, or as you can see, we have a lot of water on the earth. But when we have land, so those are tropical countries, and the weather there, it's well, it's interesting because there are a lot of there are changes. We have jungles, we have deserts between the two tropics. But between this area, between the Arctic Circle and the Tropic of Cancer, in this area is where most of people lives. So in this area we have almost everything. We have India, we have China, we have Europe, we have the United States. So I think 70 or 80% of human population live between the Tropic of Cancer and the Arctic Circle. Well, this is what happens. Probably because it's easier, because the temperatures here are not as warm as in tropical or the, well, I don't know why, but most of people are concentrated between these two lines. And seasons happen because of this angle, okay? Because when we are facing in the northern hemisphere, when we are facing the sun and the sun rays are almost perpendicular, then we have summer in this northern hemisphere, and we have winter in the southern hemisphere, because the angle of the sun rays are not perpendicular to that. So that's the difference. If we are, if the Earth revolves around the sun, so there's a time in which it's the other way around. So the angle, the sun rays on the northern hemisphere are like this. So this is winter in the northern hemisphere, and this is summer in the southern. So it doesn't have to do with the distance between the Earth and the sun. It has to do with the angle of this axis and the angle that the sun's rays, when they are perpendicular to the surface, we have summer. When they are not perpendicular, we have winter. So that's it. The closer we are to the Arctic, to the North Pole, the less perpendicular the angle is. So here we don't have light. So here in winter, as you can see, there is no light. So that's why we have darkness for 24 hours. We don't have a sunrise in the North Pole in winter. But on the other hand, in summer, in the South Pole, we have 24 hours of sun because there is no night. Okay. And there is a moment in which we have the same amount of solar radiation on the north and the south hemispheres. So this is the equinox. So that happens on March the 21st and September the 21st. Okay, so that happens on, that would be December the 21st, which is winter in the north, and that happens on June the 21st, which is summer in the north. And then we need to know the azimuth. The azimuth is the angle between this north to south line. The altitude angle is the angle of the sun on the sky. And we have I think if we look at this is the plan. And here we can see, I think I showed you that in Revit last week. We can see how in summer we have this sun path, and in winter we have this sun path. Okay, only in September the 21st or March the 21st, the sun rises in the east and sets in the west. In summer, the sun rises in the northeast and sets in the northwest. And in winter, the sun rises in the southeast and sets in the southwest. Okay, so that's important that now we have software, so we don't have to worry about this because we can just model our building with Revit or SketchUp or whatever, and we can say, okay, what's the daylight in February the 3rd? Click, and you have the sun path and all the sunlight on that specific date on a specific location. So that's great. And finally, we have PV watts. So that's the tool that we are going to use to calculate all these kind of things. I'm going to check if PV watts working, because early in the morning it wasn't working. King, New Hampshire. Okay, now it works. A few hours ago, it wasn't working. So as I told you before, we are familiar with this software, and we have to work with the tilt, Okay, so this is the angle of the wall. So 0, it's a flat surface. 90, it's a vertical surface. And this is the azimuth, which is the angle between the surface we're analyzing and the north to south axis. Those are PV parameters because this is to calculate the photovoltaic photovoltaic energy that we can get from the sun. So we will start explaining this next Monday. But by Wednesday, I want you to decide on this. And if you have your project, if you can show me pictures of your project, probably I can start asking you about this, what you want. Okay, so what kind of idea do you have for the sunlight? That depends on the use of the space, I told you, and it depends on where we are. Yeah, so it depends on the orientation of the building.